Good morning, everyone. Welcome to the second webinar of the IMath Webinar series for this semester. I am Gino Angelo Velasco of the Institute of Mathematics, and today we will be hearing a talk from Dr. Brian Hernandez. He is an assistant professor of the Institute of Mathematics. He is working on mathematical chemistry and mathematical reaction network theory. And today he will be talking about independent decompositions of chemical reaction networks and the Feinberg decomposition theorem. So by the way, I would like to remind everyone that this webinar is being recorded and streamed live on YouTube, and you are all on mute by default. If you want to raise any question in the Q&A portion, you may raise your hand and we can unmute you, or you can type your questions in the chat box. Okay, so once again, we would like to welcome Dr. Brian Hernandez. Sir Brian.
Thank you so much, Dr. Velasco, and thank you, colleagues, for attending this webinar. Again, my talk is about independent decompositions of chemical reaction networks and what we call the Feinberg decomposition theorem. This is a joint work with Dr. Ralph John L. de la Cruz, also of the Institute of Mathematics. I think it would be beneficial for us to discuss these preliminaries of chemical reaction networks. Okay, so we start with this definition: chemical reaction network, or simply CRN, or simply network. It is composed of three sets. We have script S, script C, and script R. So these are non-empty finite sets of species, complexes, and reactions where the cardinalities are given by M, N, and R respectively. So this is the first condition. We avoid loop in CRN. And then also, before I go with this condition, let me introduce this familiar notation. In this notation, 2A plus B going to 2C, this 2A plus B is the reactant, and 2C is the product. So if we are talking about complexes, then we mean reactant or product. And for the second condition, for each A in the set of complexes, there exists another complex such that one of them is a reactant and the other is a product. We associate this ordered pair AB to this familiar notation A to B. For example, we have this reaction 2H2 to O2 going to 2H2O. So this is combustion of hydrogen gas. Hydrogen reacts with oxygen, forming water vapor. In general, we can write the given reaction in this form. So this H2 can be represented by A. This O2 here can be represented by B. And C here corresponds to H2O. So 2H2 plus O2 plus 2H2O can be written more generally into this form, 2A plus B to 2C. Again, we consider this network considering only the single reaction. It's a very simple example. We have this script S to be the set containing A, B, and C. So these are the species. And complexes. So if we are talking about a complex, we have a reactant or a product. So that would be the set containing 2A plus B and 2C. And of course, we only have a single reaction, so that would be this reaction. And this is the set containing that single reaction. And we can actually represent ABC in the following form: 1, 0, 0, 0, 1, 0, 0, 0, 1. And this is obviously the standard basis of R cube. So each complex can be seen as a linear combination. So this complex here, 2a plus b, if we represent or if we consider a and b to be 1, 0, 0 and 0, 1, 0 respectively, then we can see this 2a plus b as a linear combination of this standard basis for elements of R cube. So that would imply that we need linear algebra in studying CRNs. We have a number of matrices. The first one is molecularity matrix. It's denoted by capital Y. It's an M by N matrix such that the ijth entry is the stoichiometric coefficient of species xi in complex CJ. So again, M is the number of species. So in our example a while ago, we have A, B, and C as species. So that would be M equals 3. And N is the number of complexes. There are 2 complexes, so N is equal to 2 in our example a while ago. And this incidence matrix, we denote that by IA. So it's an N by R matrix such that the ijth entry is the following. -1 if the complex is a reactant in Rj, and it's 1 if the complex is a product in the reaction Rj, and 0 elsewhere. And we have this stoichiometric matrix, so it's denoted by capital N. R is the number of reactions, so it's an M by R matrix given by the product of these 2 previous matrices. We have a number of terms, reaction vectors. So a reaction vector for a given reaction. So that would be the difference between the product and the reactant. We also have stoichiometric subspace, capital S. It's the linear subspace of R to the M being a vector space over R, given by this is S is equal to the linear span. Again, it's the linear span of the reaction vectors. We have the rank of a network, so that would be S. It's the dimension of the space, which is also equal to the rank of the matrix that we have seen earlier, the stoichiometric matrix. We say that 2 vectors in R to the M are stoichiometrically compatible if the difference is an element of the stoichiometric subspaces.
Sir Brian? Sorry po. Sorry sa istorbo po. May ano lang, may message lang po. Medyo mahina daw po ata yung audio. Kung pwede daw po palakasan. Thank you.
Salamat, sir. Hello? Hello, sir? Malakas-lakas na po ba? Malakas na po ba kaya? Okay naman po. Okay, so we consider this example. We have this network. So this network has 5 reactions. The first reaction is x1 to 2x2. And the second reaction is 2x2 to x1. The third one is x1 plus x3 going to x2. The fourth one is x2 to x1 plus x3, and then the last reaction is x2 to x3. So there are 5 reactions in this CRN. So the first matrix Y is given by the following. So it's indexed by M and N. So these are the species, and these are the complexes, as we may see here in the CRN. And for the first column, we consider this first complex. So this complex is x1. The stoichiometric coefficient of x here in x1 is 1, and the rest is 0. And then we're going to do that for each complex. And then we also have this I sub A. This is the incidence matrix. We consider these reactions, and the rows are the complexes. So the complexes are again x1 to x2 and so on. So for the first reaction, we have x1 to x2. So x1 to x2, x1 is, of course, in the first reaction, it is reactant, so that would be -1, and 1 to x2, and the rest is 0. And then you're going to do that for each reaction. And if we multiply y and I sub a in that order, then we have the following matrix, which is the stoichiometric matrix. And we can check that the rank of this CRN is equal to 3. Okay, so we have a number of terms again. We have CRN. So these CRNs can be seen as graphs, as we can see in our definition of CRNs. Complexes can be seen as vertices, and on the other hand, reactions are edges. And connectedness, there is a directed path between two vertices, Ci and Cj. So again, Ci and Cj can be seen as vertices, and the reactions are edges. So connected means there is a path, a directed path in particular, between two vertices, Ci and Cj. And connected component, so any two vertices of a given subgraph are connected. And the linkage classes, so these are precisely the connected components. I will not discuss formally what weakly reversible CRNs are, but I'm going to describe in this particular examples. So these are three weakly reversible CRNs. This first weakly reversible CRN, so we consider that if we consider two vertices or two complexes in this network, say A and 0, there is a directed path from 0 to A. It's obvious. And then you can actually go back from 0 from 0 to A, you have a path, and you can go back to 0 using this path. A to B plus C, and then B plus C to 0. So these are another weakly reversible CRN, and so on. So for each two vertices, there is a path from one vertex to the other, and then you can go back to the other vertex. We have this very important formula in CRNs. We have the deficiency. It's denoted by delta. It's n minus L minus S, where n is the number of complexes. Again, the complexes are either a reactant or a product. Number of complexes, so that's n. L is the number of linkage classes. S is the rank of the network or the dimension of the stoichiometric subspace. In our example, we have this network with 5 reactions. The deficiency is 0. N, number of complexes, so that's X. So there are 5 complexes. And linkage classes, so there are 2 connected components, 2. And then S, we have computed earlier that the rank of the network in this particular example is 3. So the delta, which is a deficiency, is of course 0. Okay, so we have a set of terms again. Species formation rate function, or SFRF. It's f of x, which is equal to n times k of x. Wait lang. Hindi ko pa pala ito na-define. Parang may na-omit akong definition. Okay, unahin ko to. Kinetics, a kinetics K for a CRN. So you basically have a network, and we assign to each reaction this rate function Ki, which sends to a non-negative real number. And then a chemical kinetic system, you have a CRN, which is composed of these 3 finite non-empty sets. And then you're going to endow that with kinetics. And then examples would be this 2, power law kinetics. So kinetics of the following form. So each reaction, there corresponds this assignment. So capital K sub Ix is given by the following. And we have this mass action kinetics. This is particular case of this power law kinetics here. In this case, the kinetic order matrix, or these exponents, are precisely the stoichiometric stoichiometric coefficients of the given in the given CRN. And we have the following species formation rate function, SFRF. So it is f of x. This is equal to n times k of x. This is equal to the summation of this quantity here. So for each reaction, you're going to get the, this is the reaction vector for that particular reaction. Then each reaction, there corresponds this value here, the kinetics for that particular reaction. And then you get the sum, so that would give you f of x, which is precisely dx over dt is the ODE, or ordinary differential equation of the chemical kinetic system. The equilibrium or steady state is just a zero of f. A CRN is said to admit multiple equilibria if there exists positive rate constant such that the ODE system admits more than one stoichiometrically compatible equilibria. So we can see here that in CRNs, we also consider differential equations, in particular these ordinary differential equations, and then we are solving this differential equations, and that would give you a study in equilibria, stability, and so on. Consider this a simple example. We have this ODE. We have this ODE for the given system, which is governed by the mass action kinetics. So we have this differential equations, and this is a corresponding network, and you can actually get a graph from MATLAB. So we have we can see here that the species concentration, the species here are A1, A2, and A3. So the species concentration change over time. And as we can see here, an equilibrium would be 2, 1, and 3. And you can actually compute it here in the given ODEs. In our previous example with 5 reactions, say this is capital F, the kinetic order matrix, and we say a while ago that f of x is equal to n times k of x. N is the stoichiometric matrix, and k of x corresponds to the kinetics. And this is the stoichiometric matrix, and we can actually compute k of x using this f here, and the corresponding ODE would be given by the following. And one applications of CRNT is studying ODEs using networks. And if we equate each to 0, and then you can get the values x1, x2, x3 such that these expressions or these components are 0. And we can actually solve for the equilibria of the system. We have this important theorem in CRNT, deficiency zero theorem. Here, for any CRN, of course, with deficiency 0, the following statement hold. The first one is, if the network is not weakly reversible, then for arbitrary kinetics, the differential equations for the corresponding reaction system cannot admit a positive equilibrium. So this is a very important theorem. Of course, for networks with deficiency 0. I omitted the second statement because it's a very long theorem. We consider this third statement. So if the network is weakly reversible, then for mass action kinetics, regardless of the positive values, the rate constants take, the resulting differential equations have the following properties. There exists within each positive stoichiometric compatibility class precisely one equilibrium, and that equilibrium is asymptotically stable. There is no non-trivial cyclic composition trajectory along which all species concentrations are positive. So here we can see that, of course, this is very useful for deficiency zero networks. For the first condition, for those networks with such that they are not weakly reversible, then this is the conclusion. And for the third one, for weakly reversible, but we have to consider mass action kinetics. And then this is the conclusion. Okay, so we now go to the compositions and independent decompositions of CRN. So of course, we have to define what decomposition is of a network. We have the following definition: a decomposition of a network script n is given by these subnetworks. So you actually decompose the network in terms of partitioning the reaction set. So again, we have a network, and that network is a set of finite reactions with two properties. And then this decomposition of a network is induced by partitioning the reaction set into this K reaction sets. For the corresponding stoichiometric subspaces, we have S is equal to this sum, S1 plus S2 until Sk. And then we now have this definition for independence. A network decomposition N given by this N1 union N2 union and so on until Nk is independent if its stoichiometric subspace is a direct sum of the stoichiometric subspaces of the subnetworks. So that would be the definition of an independent network decomposition. So you basically have a decomposition, and then if you consider, if you have the stoichiometric subspace of the whole network is equal to the direct sum of the stoichiometric subspaces of the subnetworks, then you have an independent decomposition of the network. Now we have this decomposition theorem, which was due to Feinberg in the 1980s. This is one of the motivations of our study. We have the following. So let P of R this partition of the reaction set, which induces a partition of the network, and let K be a kinetics on N. Then capital N, if capital N is given by this decomposition of the network in terms of this partitioning of the reaction set. Then, and we consider this E plus here, E plus NIKI, this is equal to the set of all X. These are the positive equilibria of the given subsystem with the underlying subnetwork and the given kinetics. Then we have this containment, that the intersection of the equilibria sets of this subsystem is a subset of the equilibria set of the whole network. Now, if the decomposition is independent, so we emphasize independence here, then we have this equality. Equality holds when we have this added condition of independence. Now, there are several natural questions regarding independent decompositions. Number one, given a CRN, can we always find an independent decomposition? The answer is yes. And we have always the trivial independent decomposition. So that would be decomposition where there is only one subnetwork, which is the network itself. And number two, do we have a necessary and sufficient condition for the existence of non-trivial independent decomposition of a CRN? And correspondingly, by that, say a theorem, do we have a method of finding such non-trivial independent decomposition for us to exploit this theorem here? We want the independence for us to study this equilibria sets with equality. So that would be the motivation. And number three, how many independent decompositions are there in a CRN? Are there any bounds on the number in general? I will not focus on number 3, I will just focus on number 2. Number 3, we had a formula for the number of independent decompositions. This is given by, we will use the Bell number for us to get the number of independent decompositions. That's in term of what we call what we term to be prime independent decomposition. So I will just focus on number 2. We have the following definition. Let R be this set of of vectors such that the span of R is of dimension P. And suppose that we have this set is a linearly independent set. Now, as we notice here, so you initially have this R containing M vectors, and we just pick P vectors here. So we have P to be less than or equal to M, where this set is linearly independent. The coordinate graph of R is the undirected graph G given by VE, such that this V here containing, we rename this vectors to be R1 is renamed as V1 and so on. RP is renamed as VP. And edge set E, we have the following VI and VJ will give you an edge if in E, if and only if there exists K greater than P. K greater than P with RK to be equal to the linear combination of this RIs here in this linearly independent set, such that both AI and AJ are non-zero, which correspond to this VI, VJ. So that would be the definition for the coordinate graph. We have this main result theorem. So let R be a set of finite vectors, a finite set of vectors. An independent decomposition of R exists if and only if the coordinate graph of R is not connected. So this is a necessary and sufficient condition for us to get this independent decomposition if it exists. Okay. And after giving this theorem, we have this method of finding independent decompositions of CRNs. Number 1 is to get the transpose of the stoichiometric matrix, which we denote by NT. And then let's find a maximal linearly independent set of vectors, as we have seen earlier, which will form a basis for the rough space of NT. And so on. So I will just give you an example to illustrate this method. Let's consider this example. This is the yeast fermentation pathway by Curto et al., which can you see in the book of Voigt, where ethanol is being produced. And from that model, you can actually get this network. We consider the generalized mass action model of anaerobic fermentation pathway of Saccharomyces cerevisiae of Curto et al. The CRN is courtesy of Arceo et al. So Arceo et al. So this is Dr. Arceo of IMath. We have these 13 reactions, and which was based, of course, from the given model that we have seen earlier. Then the corresponding stoichiometric matrix. So we actually have this 2, 4, 6, 8, 10, 12, 13. There are 13 rows of the matrix because there are 13 reactions. And then you just get the, so you have for the first row, you have x1 plus x2 minus x2. So that would give you x1 as the reaction vector. And that would correspond to 1, 0, 0. 1, 0, 0, 0. There are 5 species here. And so on. You will do that for each reaction. So this is the stoichiometric matrix of the given network. Now, let Ri be the ith row of the matrix. Observe that the rows R1, R2, R3, R4, R8 form a basis. So that would be the next step after getting the transpose of the stoichiometric matrix. So you will have to get a linearly independent set. So in this particular example, we consider R1, R2, R3, R4, and R8 as the elements of the basis. And then we have the following relations. Nakuha natin yung R1, R2, R3, R4, and R8. And then for the remaining vectors, we have R5, R6, R7, R9, and then until R13. So we can actually write this reaction vectors here in terms of the linearly independent elements set. And then we now represent, or we relabel R1, R2, R3, R4, R8 respectively by this V1, V2, V3, V4, V5. The linear combination here then contributes the following edges to the coordinate graph G of R. So in our example, R6, so R6 is negative R2, negative R1. So we have V1, V2 as an edge. And then for R10, you have the following, and then you have this as an edge. These are edges. And then for R11, VI, VJ, we have IJ1, 2, 4, 5 as the indices. And this is a coordinate graph for our example for the yeast fermentation pathway of CRN. There are two components, and from this method, then we can get this. There are two maximal components of G for G, which induce the following independent decomposition of R. We have P1 and P2. These are the this would be partition of R for us to get an independent decomposition. So thus, the CRN of the given model has a non-trivial independent decomposition given by this partition. And we also have these implications of the FDT. So a while ago, we considered FDT, and that FDT gives us a relationship. Let's go back to FDT. Yeah, this is FDT. So this theorem gives a relationship between the set of equilibria of the whole network and that of the subnetworks and the whole network. Now, if this is equality, of course, we should have independent decomposition. Now, what are the implications of that theorem? The first implication is that if you have a large system, then you will be able to get the same, and you were able to get the same positive equilibrium for each subnetwork, then it must be a positive equilibrium of the whole system and vice versa. And then number two, if at least one of the independent subsystems mean subsystems obtained via independent decompositions of the underlying network with the endowment of the kinetics for those subnetworks cannot admit a positive equilibrium, then so is the whole system. That is the set of positive equilibria of the system is empty. And number three, we have if one subsystem has exactly one positive equilibrium, then the whole system has at most one positive equilibrium. And the number four, we can use FDT to provide an upper bound on the number of positive equilibria of the whole network by the use of the independent subnetworks. So these are some of the implications of the FDT. Actually, we submitted this paper to one of the Springer journals, and one of the comments is that Oh, I forgot. Sorry, I forgot the comment. Yeah, the comment um, for this particular implication. Sorry, I forgot that at the moment. Okay. Another example is this one. So we have this influenza virus model. So we have this figure um, by Backham. So we call this the Backham model. This is the Backham model, and this is the network. And these are the independent subnetworks, and these are some of the information regarding those networks. And this network consists of four reactions, and N1, the first subnetwork, is given by R1 and R2, and the second one is given by R3 and R4. So consider the BACA model with three variables: an infected susceptible target cells given by the variable T, infected cells given by the variable I, and infectious viral titer given by the variable V. Here, an infected target cells become infected. So an infected become infected at this rate. And infected cells die spontaneously. So in addition, virus proliferates and dies at the rate of P and C respectively. So this is the network, and these are the subnetworks. So as you can see here, um, the rank of the network, so you have 2 plus 1, 2 plus 1. So these are the two subnetworks, N1 and N2. The corresponding stoichiometric subspaces are 2 and 1 respectively. 2 plus 1 is equal to 3. So 3 is the stoichiometric subspace dimension of N of the whole network. So this will be, of course, an independent decomposition of the network. Okay. So this analysis will give us that this network does not have the capacity to admit multiple equilibria. Um, in this example, we have to use the deficiency zero theorem. So remember, in the deficiency zero theorem, so let's again look at the deficiency zero theorem. In the deficiency zero theorem, the following statement holds. So if the network is not weakly reversible, then for arbitrary kinetics, differential equations for the corresponding reaction system cannot admit a positive equilibrium. Okay. So for deficiency zero and it is not weakly reversible, then for any arbitrary kinetics, there is no equilibrium, a positive equilibrium. Yeah. Um, so we use this N1 here. N1 contains R1 and R2. R1 and R2, the deficiency of this subnetwork is 0. So since the deficiency of this network is 0 and this is not weakly reversible, then based on the deficiency zero theorem, there is no positive equilibrium. And if we get the intersection of the sets of equilibria of the subnetworks using the Feinberg decomposition theorem, where we have this independent decomposition. So you have E1 and E2 here corresponding to the two subnetworks in the given independent decomposition. Then we have the conclusion that it cannot have a positive equilibrium of the whole for the whole network. It can't have a positive equilibrium. Another example is this one. So consider a generalized mass action model of purine metabolism in man. This is given in one of the books of Voigt, Computational Analysis of Biochemical Systems. We take into consideration the total representation with the following reactions provided in the supplementary material of Arceo et al. There are 42 reactions, so there is actually an independent decomposition for this particular example. So as you can see here, there are 42 reactions, and this is um, a large network to handle. So what would be the importance of our work? So we will consider subnetworks, and these subnetworks may help us to study um, a large network, and we can study the equilibria properties of those networks. For Of course, in particular, we have this large network. We have this summary. So definition. So a network decomposition N, so given by the following, is independent if its stoichiometric subspace is equal to the direct sum of the stoichiometric subspaces of the subnetworks. And we also introduced this with what we call the Feinberg decomposition theorem, or FDT. We have this decomposition of the network, and you have this equilibria sets of the subnetworks. If you get the intersection of the equilibria sets of the subnetworks, then you will get this equality with respect to the equilibria set of the whole network, given that the decomposition is independent. And as we can see here, say we have three equilibria sets here, three networks, and three corresponding equilibria sets. We have E1, E2, and E3. Then this is the intersection. Now, in the case where this is equality, so this intersection here will be the equilibria set for the whole network. Yeah, so this will be the equilibria set for the whole network. So that would be useful. That can be useful for us to study the equilibria set of the whole network. And actually, as you can see here, dito sa sa mga subnetworks dito, pwede actually mag-iba yung mga species. Kasi halimbawa, kinonsider natin halimbawa paghiwalayin yung halimbawa may 4 na reactions tapos tig-2, possible doon na doon sa isang subnetwork na wala yung isang species. So you can actually analyze this by projecting the species space of the whole network to the subnetworks with respect to the kinetics of the whole network. So with respect to the whole network siya, pababa dun sa subnetwork. So we are allowed to do this equality here, as was introduced by Feinberg. So that would be all. Thank you very much for listening.
Okay. Thank you very much, Dr. Brian. Let's give him a virtual round of applause.
Salamat po.
Okay, thank you. Now the floor is open for any question. I will now allow participants to unmute themselves. Do we have any question from the audience? Question? Yes, may naka-raise po si
Ma'am Vicky.
Ma'am Vicky po. Yes, Ma'am Vicky.
Hello, good morning, everyone. Good morning, Sir Brian.
Good morning.
Thank you for that talk. I would like to clarify a few things. So the first one, regarding din sa statement mo on this summary. So you said, so is it correct na if I look at the network differently with respect to different species, you said something like that, would the decomposition change? Yeah, okay. And in effect, mag-iiba din ba yung result, yung number of positive equilibria and so on?
Yeah. Actually, ma'am, lagi tayong with respect to the whole network, and then that whole network is decomposed into subnetworks. So laging ganun kasi may time nga na nawawala yung species. So yung merong projection from the space of the whole network papunta dun sa subnetwork. Kasi nga dun sa, as you can see in the species formation rate function. Yeah. Ito ba yan? Species, yeah. Dito sa species formation rate function, so kasi pinag-aaralan natin dito yung equilibrium, so this is equal to 0. Zero to kapag kinukuha natin yung equilibrium. Now, kasi meron ditong species, so merong projection from the whole network papunta dun sa subnetwork para magawa natin. Hindi siya, kasi kung titingnan mo nga yun, minsan, kung titingnan mo siya, pag nag-start ka dun sa subnetworks, may mga nawala minsan, pero minsan hindi naman nawawala. Pero dapat tumingin tayo dun sa sa whole network. So, katulad ng example naman natin dito, ito ba yung example ko na yun? Nawala ba dito yung hindi ko pinakita. Meron, pwedeng mawala yung may mawala na species dito. Katulad nito, pag kinonsider mo yung yung R3 at saka R4 na wala yung A1. So may projection kang gagawin from the set of the networks, lagi set of the whole network, laging set of the whole network pababa dun sa dun sa subnetworks para so that we can be allowed to do this SFRF.
Okay. Ibig sabihin, follow-up question na. Ibig sabihin ba nun ay, I guess related ito dun sa question number 3 dun sa list mo. Ibig sabihin ba nun ay isa lang yung pwede kong way ng pag-decompose given a big network, or pwede pang magkaroon ng ibang decomposition?
Ito yun, ma'am. Itong number of yeah, actually, pwedeng marami, ma'am, na katulad nito, may maliit lang kasi yung example na kinonsider ko dito. Yeah. For example, ipakita ko na lang yung isa, yung sa paper na sinabit namin. Ito. Ito ba yun? Saan yan? Yeah. Katulad nito, this handle network, palakihin lang natin ang konti. This handle network, we have N1, N2, N3, N4. These are N1 union N2 union N3 union N4. That would give you this decomposition of N. And that would be one independent decomposition. Another independent decomposition is N1 union N2. And then N3, N4. So it's also an independent decomposition. And another independent decomposition is N2 union N3, and then N1 union N4. So you can actually get several independent decompositions based on the network.
Okay.
Yes, ma'am.
Okay. Yeah. Another question, kung is it also possible to determine yung number of positive equilibria kahit doon sa case na equal yung nandun sa conclusion ng theorem? Possible ba yun?
Actually, dun sa theorem, very useful ito para malaman kung kung wala siyang equilibrium. Kasi kung yung isang subnetwork wala ng equilibrium, wala ng equilibrium or positive equilibrium yung buong network. Tapos kung dun sa several networks na yun, yung isa sa kanila may isa na equilibrium, then at most yung masasabi natin, dun sa number of equilibrium of the whole network. Actually, hindi natin malalaman yung number of
Okay.
equilibria. So, kumbaga pwede din nating malaman yung bounds kasi may mga papers na nagko-consider ng bounds. So dito, kapag yung yung may isang subnetwork doon na may 3, halimbawa may finite tapos 3 yung number of equilibria. Then yung whole network may at most 3.
Okay.
Yun
Yeah.
lang ma'am yung masasabi natin
Yeah.
about the ano.
I guess okay pa din siya kapag very big yung network mo,
Yep.
di ba? Yeah. Okay. Thank you
Thank you
for
ma'am
the
for that question.
answers.
Okay.
Thank you, sir.
Thank you po, Ma'am Vicky. Yes, thank you, Brian. Now, we have another question from Sir Aurelio de los Reyes, sir.
Good morning. Good morning, Sir
Morning.
Brian.
Morning po, sir.
Thanks sa talk. Meron lang akong specific question dun sa influenza model ni Backham. Nung ginamitan nyo ng network analysis, ilang equilibrium yung nakuha? Kung meron bang multiple equilibria na nag-exist o isa lang?
Wala po, sir.
Walang nakuha?
Wala.
Ano kaya yung implication nun, practical implication pag walang equilibrium yung system?
Pag walang equilibrium yung system, kasi ito pong study of equilibria. So itong mga species dito, yung mga species dito na TVI, so these are the, katulad nito, number of infected cells na kung saan, number of infected cells na kung saan nagbabago siya over time. So yung iba namamatay and so on. So number of infected cells. So kung wala siyang positive equilibria or equilibrium, paano ko nga i-explain? Pag wala siyang positive equilibrium, yung number of cells pwedeng nababawasan over time.
Yeah, so parang ang nangyayari, hindi rin pwedeng mangyari na periodic, no?
Yeah.
So pwedeng random, so wala kang makukuha. Pero later on, kung cells kasi, merong limitations, pwedeng mamatay sila lahat eh. So curious lang ako na bakit wala siyang nakuhang equilibrium using CRNT approach at ano kaya yung practical biological implication nun. Tapos may general question ako sa CRNT approach. Well, ang unang comment ko is ang maganda dito, it's parameter free. So na-analyze yung network without regard to any specific values of parameters. Pero pag ginagamit mo siya sa particular biological system, yung values ng parameters are very important kasi doon mo nalalaman yung bifurcation at ibang yung dynamics ng system. So pag meron na bang study na nirelate nila yung decomposition sa existence ng bifurcation, for example? Kasi sige, go.
Meron na po mga study about bifurcations, pero in this particular decomposition, kasi ang nangyari kasi po sa decomposition, this was a result by Feinberg, yung tinawag nating Feinberg decomposition theorem. That was a result of Feinberg in the 1980s. Tapos, kumbaga, hindi na siya na-prosper. Hindi siya napansin na sa CRNT community. Actually, meron kasing more na mathematics of reaction network. So dito, nagkakaroon ng series of webinar yung ating mga experts sa CRNT worldwide. And when Dr. Lau presented in that seminar, we have discovered that yung mga experts natin sa CRNT outside the Philippines or abroad, hindi sila familiar actually sa decomposition. So I think maganda na i-revive yung decomposition. Baka mag-prosper itong decomposition po. So yung wala pa pong masyadong study about decomposition, lalo na sa bifurcation analysis po.
Yeah, na-curious lang ako kung paano yun marirelate doon eh. Kasi pag bifurcation analysis naman, very particular parameters yung tinitingnan eh. at yung parameter space. So ano kaya ang magiging itsura noon sa parameter free na CRNT approach? So baka merong merong relationship yung network, yung smaller sub-network from a bigger network when it comes to bifurcation ng system.
Sige,
Yun
sir.
lang.
Yeah, thank you po, sir. Siguro po yung first step ko dito ay tingnan yung studies about bifurcations. And yeah, siguro baka po may relate siya sa decomposition.
Oo, kasi meron din siyang relationship sa existence ng multiple equilibrium. So, pag marami kang equilibria, for example, tulad dun sa carbon cycle mo na may mga tipping points. So, those are actually bifurcation points. So, baka lang at some point matingnan yung relationship ng smaller subnetwork at yung bifurcation.
Thank you po.
Okay, thank you. Yun lang, Sir Gino.
Okay, thank you, Sir Au. Okay, and we have one more question from ito si Seth, Mr. Mesosa. Pasok po.
Okay.
Ito. Ay. So, tinype niya yung question. So, good morning. I would like to ask some questions. Number 1, what is meant by equilibrium and positive equilibrium here exactly? What I know about chemical equilibrium, although I am not sure about it, is that the forward and reverse process in a reaction may happen at the same rate or are both spontaneous.
Yeah. That would be a specific case. More generally, we have the following definition. We have the following definition. We have the species formation rate function. F of x is equal to, this was previously discussed. We have this, for a given reaction, you have to compute for the reaction vector. That would be product minus reactant. And then each reaction corresponds to a kinetics. And then you get the sum. And then you have dx over dt to be equal to f of x. So the solution of the equation, if this is equated to 0, that would give you an equilibrium or a steady state of the network. And what we mean by positive equilibrium, each component of the vector, a vector in the set of equilibria, is positive. So that would be the definition for an equilibrium being positive. Yeah. Thanks for that question.
Yes, and his second question is, if in a complex reaction network an independent decomposition is obtained, does it mean that if a reaction went differently from what was modeled, that is not, for example, not enough reactants, mutations happened, we can more easily trace what happened to the reaction, or does it have another physical implication or interpretation?
Physical interpretation. Actually, based on the, lagi muna ako naka-base dito sa theorem of Feinberg. Ang implication nito ay with regard to the number of the equilibria of the whole network. So you can have a bound or a specific number for a given network, for a given system with this is with the CRN as the underlying network. So regarding sa other implication, siguro I will look into that. I will specify the details na kung ano pa yung pwedeng maging interpretation nito. Yeah, siguro gano'n na lang yung magiging sagot ko ngayon.
Okay. Yeah, thank you. May quick comment ata si Ma'am Kayen.
Sige po.
Yeah, good morning, everyone. Thank you for joining today's webinar. Thank you, Brian, for that talk. Acknowledge ko lang ulit si Ralph de la Cruz. Dr. Ralph de la Cruz, for those who do not know Ralph, is also a member of our institute. He's with the IMath. He's a young PhD, a very active researcher who belongs to the matrix analysis and linear algebra group. So I was just going to say very quickly that this particular joint study that Brian presented is I'm very happy about it, and I hope it inspires many, because in one study I think that we came out with I did a collaboration with Sir Ed and Justine Villar, and we were saying that topics like this, you can either just look for more applications or go deeper into the theory. And it's very nice that going deeper into the theory, we get to collaborate with colleagues in other areas, like in this case, matrix analysis. No? So I hope this will inspire others to do that as well. Parang the goal anyway of our webinar series is also to show everyone what's currently going on research-wise among our colleagues in the Institute of Mathematics, to maybe show others what directions they may take, inspire others, and invite others to join us in collaborative work. And I mentioned earlier Dr. Ed Mendoza. I would like to acknowledge his presence this morning at the webinar, and it is really morning where he is now. He's in Munich, and I think it just hit 4 a.m. Tama ba ako, sir? It just hit 4 a.m. in Munich, so we're very happy that you're able to join us, sir. He pointed us first in this direction in CRNT. I think it was 10 years ago already, sir, no? During the time of Patrick Lubenya and now Dr. Justin Villar. And now we have there's a very active group doing CRNT. And as Brian mentioned, medyo nare-recognize na rin sa international CRN community. So I would like to acknowledge Dr. Ed for that. So thank you very much, sir, for joining this webinar as well. See you more. Thank you, Gina.
Thank you, Ma'am Karen.
Thank you.
Thank you po, Doc Ed.
Thanks, sir.
Ito pala si Doc Ed.
Yes, thank you. Are there any other question or comment? Okay, if we do not have any more question, you can also email Sir Brian. Maybe Sir Brian, you can type in your email address for some of the guests if they have any further question. And otherwise, I would like to thank everyone for coming, for being here, the Modeling and Applications Group, and particularly to Dr. Brian Hernandez for giving us this very nice talk. So our next webinar will be on March 22, and we'll hear from a speaker from the Matrix Analysis and Linear Algebra Group. So until then, goodbye, see you, and enjoy your lunch.
Thank you, Gino.
Thank you, Sir Gino. Hi.
Thanks, Brian. Thanks, everyone.
Thanks,
Have
Brian.
a good week.
Salamat po sa inyo.
Good morning, Sir Ed.
Good morning po, Doc Ed.
Hi, Sir Ed. Morning na morning talaga.